Good afternoon. If y'all could crack your texts open, we're going to get started right where we left off yesterday. Question 2111. Just finished last class with 2110. Talking about what happens when you take a cold lens outside. Now move on. Question 2111. Considering some more processes that we don't usually think of as happening. So, a couple of questions that we've already sort of answered. 2111. Can I make solid water turn into gaseous water at -1 degree Celsius? Well, we take a look at the phase diagram. I don't have it drawn up here anymore, but if you flip a few pages back, you'll find the answer is yes. Now, under what types of conditions is this reaction going to occur? Will it be spontaneous? The vapor pressure of the solid is greater than the pressure of gaseous water. So those are the conditions that we need in order for the sublimation of water to occur. And of course, for sublimation to happen for water, we have to be below 0 degrees C because our G-state diagram, the one we took such a close look at yesterday, tells us so. Little Roman numeral 2. Gaseous water to liquid water, above what we consider the boiling point of water, 101 degrees C. Now can we make this happen? Given our analysis of vapor pressure yesterday, the answer is also going to be yes. What sorts of conditions do we need for this to occur? Well, in this case, I want the vapor pressure of liquid water to be less than the pressure of gaseous water. And in that case, I can make this reaction occur. So there is a second part to this question. What about standard state conditions? So if I take a look at my phase diagram for water and I follow that 1 atmosphere line around, am I ever going to be able to sublime water at that temperature? 1 atmosphere external pressure. Nope. So, standard state, no. Because at the standard state, pressure of water is too high. Similarly, take a look at this reaction here. Gaseous to liquid water. We know at 1 atmosphere, the vapor pressure for water, well, at 100 degrees C, 1 atmosphere is the vapor pressure for water. So, under these conditions, at 1 atmosphere, it's impossible for me to make this happen. So once again, under standard state conditions, this reaction is not going to occur. And we know all this information from our table. We can sort of infer the first two parts, but we have to have some sort of tabulated information to tell us whether or not this can occur in the standard state. So there's question 2111. Moving on from there. Well, does anyone have any questions on this? Vapor pressure stuff, looking back at our diagram that we looked at yesterday. Sort of a quick recap. Okay. So, question 2112. Potassium chlorate decomposes into KCl, simple salt, and elemental oxygen. We're given the heat of formation and the standard entropy, standard heat of formation as well, or potassium chlorate. Now, we're asked to show that this reaction is spontaneous. And we know that the sole criterion for spontaneity is neither heat of formation nor standard entropy. Gibbs free energy, delta G, is what we have to solve for of this reaction in the standard state. So we're going to go ahead and we're going to do that. Now, well, as you guys flip back to the table into chapter 20, take a look at the 4 values that we're going to need to fill in these 4 holes. I know one of these actually right away off the top of my head. What do I know here? 0 for something? Oxygen, most stable allotrope of the oxygen element. O2, dioxide gas. Heat of formation 0. That one's easy. So what's the heat of formation for KCl right off the table? Enthalpy. Negative 436.7. Okay, and what's the standard entropy for oxygen? That's not going to be 0, remember, because we have a point from which we can measure all entropies. What's that? 205.1. And standard entropy for KCl. Yeah.
Is this table going to be provided for us on the exam?
You won't have an entire copy of the table. Dr. Horvath will just give you the information that you need, should you need it. So he'll tell you, instead of just giving you, for example, in 2112, he gives you standard heat of formation and standard entropy for KClO3. He'd give it all to you. And then he'd tell you to compute G, or to talk about the spontaneity, in which case, compute G. What's that?
82.6.
82.6. So, all we're going to do in this case is apply Hess's law twice to get change in enthalpy and change in entropy of this reaction in the standard state. Plug this in to what we know, delta G equals delta H less T delta S. We're given temperature, 25C, 298K. And we can go ahead through and solve. So, those of you with calculators, if you could please help me out. We'll write out enthalpy first. So if you're typing a line into your calculator, this is what it should look like. Remember, you have the double negative here. Negative 91, is that a hard number or is that a 0.0? Negative 91, sure, we'll say 0.0. And I'm sort of lazy about writing my units in here, but make sure you know this is standard enthalpy, so kilojoules per mole is the unit. Okay. Now, let's talk about change in entropy of this reaction. 494.3, I believe it. 494.3 what?
Joules per mole.
Okay, so just by looking at these two numbers, I've already proven that this reaction is spontaneous or not spontaneous.
Don't you know temperature?
Yeah, we got it. 25C.
It's compound.
Spontaneous. At which temperatures? All temperatures. So in this case, we don't need to know, if we want to talk about this qualitatively, we don't need to know temperature at all. Because delta HR is negative, favorable change in enthalpy, bond improvement has happened. Positive, T delta S, favorable change in entropy. I'm going from 2 moles of solid stuff to 2 moles of solid stuff and 3 moles of gaseous stuff. I've increased randomness greatly. So this reaction is absolutely favored to occur and can occur at any temperature that we can imagine. Yeah?
Can we keep that in joules per mole Kelvin, or do you have to convert that to kilojoules to match the delta HR?
Whatever you like. Yeah, you don't have to, just so long as you understand that this is favorable, as is this. If you want to plug it into here, and we will in just a minute, you have to make sure that they're both the same unit. Otherwise, you're going to end up with a number that doesn't make sense.
So since, just to clarify, favorable conditions in both will ensure that it's a spontaneous reaction?
Yeah, absolutely. Okay, so the next thing that we're going to do, we can go ahead, since we're already in kilojoules per mole, if somebody wouldn't mind computing the Gibbs free energy of formation in the standard state of this reaction, please.
It's negative 238.3.
Negative 238.3. Kilojoules per mole. And this, of course, is a temperature-dependent number at 298K, 25C. Okay, so I know this reaction is spontaneous. At any temperature, it can go. Question 2113. Note that potassium chlorate, KClO3, what we have there, is stable at 25 C1 atmosphere. I got a jar of it up in my lab, just sitting there. It's not exploding. I don't see oxygen gas coming out of it. There's no KCl in there. Now, why is this so? He gives us a little bit of hint. This consideration also applies to things like wood, sugar, paper, diamond. They're just sitting there. So why doesn't this reaction go?
It has a stable structure.
Has a stable structure, okay, that's a part of it. It's a kinetic concern.
So it's not spontaneous, it needs activation energy?
Yes. So, the problem is kinetics. This reaction isn't going to run because there's a barrier for me to begin breaking these chlorine-oxygen bonds before I can create oxygen-oxygen bonds. So in order for this to work, I have to put energy in before I get all this energy out. And it's just like a piece of paper. If I want to burn a piece of paper, I didn't bring a lighter today, sorry guys. But if I want to burn a piece of paper after the semester is over, I supply some activation energy, a lighter. Now, do I have to continue supplying energy for that reaction to run, or is the paper just going to burn itself out? Correct, because I've already surmounted that activation energy. And that allows the reaction to run and continuously run, because as we know, the burning of things like paper is vigorously exothermic, so it provides its own activation energy. So, for the same reason that things like paper, sugar, which your body digests to take energy, all these things are stable until you provide for them an enzyme in your body to to digest sugar or some activation energy. Now, I'm not going to steal Dr. Horvath's thunder here. He'll show you how to overcome the activation energy for this stuff to create KCl and O2. It involves a hammer. Be in class on Monday. A little bit of physical force to overcome that activation energy. So 2113, it's a kinetic concern. You have an EA, activation energy. All right. So, question 2114. As it follows from what we looked at in 2112, is it possible to make potassium chlorate by the reaction of KCl, potassium chloride, with oxygen gas? Can we do it? Well, as I read it left to right, this reaction is spontaneous at all temperatures. So if I read it from right to left, I'm going to change my sign here. Non-spontaneous at all temperatures. Positive, delta H. Negative, delta S. That reaction's never ever going to work. So, the answer to 2114, a resounding no. Because that reaction, as I read from right to left, is non-spontaneous or anti-spontaneous at all temperatures. And we can't make those reactions go, no matter how hard we might try. We go on to mention that the industrial process for making that potassium chlorate involves taking chlorine gas and treating it with aqueous potassium hydroxide. I've done that before. You don't want to be anywhere near it. It's a very scary reaction to run because you have to use pretty high pressures of chlorine gas, which turns into hydrochloric acid in your lungs. That's why it's so bad for you. So, you can make it, but you want to do it very carefully. All right, so question 21.2, or part 21.2, equilibrium. Dr. Horvath is going to talk to you guys about that on Monday because he's got two little bulbs of N2O4 and NO2, and he'll explain to you all about how the equilibrium between them always exists and how to change that equilibrium based on temperature. Has he shown you guys those little bulbs? I think that was one of the introductory remarks when he's talking about K values. Little bulbs of N2O4 is like brown gas. One of them was brown, one of them was clear. Not yet, okay. Well, maybe he did? Okay, yeah. He shows them for like a day, first or second day of class. And we'll go back to that, and he'll put one of them in ice, and he'll show you how that affects the equilibrium between the two. That is really best described along with that visual cue, and I don't know where he keeps all that stuff at this point. I can only find the one. So, we'll jump ahead to 21.3, thermodynamic properties of a reaction system. This is the point in the semester when you realize you've been doing thermodynamics the whole time. We just haven't called it such. Now, we'll start with a quick refresher. Standard state, what are my rules quick? For aqueous species. For an aqueous ion or an aqueous molecule to be in the standard state, I think I heard someone say it, 1 molar concentration. We also use molality. Forget about that. We won't talk about it again. If I have a gas, what's the pressure of that gas have to be? 1 atmosphere or 1 bar? For our purposes, the two are equal, but remember 1 atmosphere is 1.01 bars. For a solid or liquid that is pure, already in the standard state. Now, there's one other really important thing that people always miss. Let's write it down again. This applies to all products and reactants. A lot of time when people are trying to talk about a reaction that's going on in the standard state, they just write down, I have 1 molar concentration, 1 atmosphere bar of pressure of my reactants. And that's the reaction in the standard state. No, no, no. My products as well have to be there in their respective concentrations, pressures, or phases. So, quick refresher of the standard state. Another quick refresher. We mentioned before, heat of formation. Of aqueous H plus is equal to 0. This is a reference point for all of our aqueous ions. This is very important. But you take a look, that bolded phrase, bottom of 21.9. Standard entropy as well as Gibbs free energy are also equal to 0. Gibbs free energy formation standard state, to be more specific. So, these are 3 pieces of information that we know. We can take advantage of those should we ever be faced with a problem that involves hydronium ion, or any other ion for that matter, but most of the complicated math has been done for us, so we have that information available to us. Okay, let's see here. Finally, remember that Gibbs free energy of a reaction, no standard state symbol, means that measurements may have been made under any set of conditions, so long as the reaction in question can run in those conditions. So, to be sure we know the difference between the standard state and non-standard state, we'll beat it to death. Question 21. From a Gibbs free energy of reaction standpoint, can I dissolve calcium carbonate, chalk, in water? Can I make this happen? Well, what happens when I take a solution of pure water and I put some calcium carbonate in? That does, right? I go to equilibrium, which means I've dissolved some of my calcium carbonate into its 2 aqueous ionic components. Which basically takes us right to the answer. I can absolutely dissolve calcium carbonate in water. This is all that we're asking. Spontaneously. I just put it in water. Some goes in. It's easy. Now, how about from a delta GR standard state standpoint? So if I start off initially, calcium carbonate in the standard state, it's solid. If I start with 1 mole calcium ion and 1 molar carbonate ion, am I going to be able to dissolve any calcium carbonate in this system? Think about the KSP for calcium carbonate. So for this reaction, any reaction in the standard state, Q equals 1. K for this reaction. KSP calcium carbonate, what's that number? 6.2 times 10 to the minus 11? 9. Still low enough. So, Q, a little bit larger than K, yes? Which means which reaction, or which way is this reaction going to go? To the left by a very large landslide. So, according to a Gibbs free energy of reaction in the standard state standpoint, there is no way that this is ever going to happen. As a matter of fact, I can't even make a solution like this. 1 molar calcium, 1 molar carbonate ion. Because they would slaughter each other. Give me some calcium carbonate. So, yes and no respectively are going to be your answers for question 2121. Now, we've made a couple important observations here. For any reaction that I run in the standard state, Q is always going to be equal to 1. No matter how I phrase it, if all my concentrations and all my partial pressures are equal to 1, Q is equal to 1. We notice that on the next page, but it's good that we saw it here as well. Okay, so we'll start off with a hypothetical reaction. 2 moles of aqueous X plus 1 mole of gaseous Y gives us aqueous Z. All right, so if this system is initially in the standard state, we know concentration of X, 1 molar. Partial pressure of Y, above my aqueous system, 1 atmosphere. Concentration of Z, also 1 molar. Remember your products. All right, so 3 conditions we could have. Delta G is negative. We know this corresponds to a favorable change in free energy. And we know that this is spontaneous. What can I say about K then?
K is greater than 1.
K is going to be greater than 1. Because for a spontaneous reaction in the standard state, I know that the concentration of my products comparatively is going to outstrip the concentration of either one of my 2 reactants. Well, both of my reactants, as we see it phrased in a K expression. Now, the opposite. We have a positive change in Gibbs free energy. This is non or anti-spontaneous, the same thing. K, of course, is going to be less than 1 because this is going to be a reactant-favored reactions. I know that as I let this reaction run in the standard state that I will end up with greater than 1 atmosphere pressure Y and greater than 1 molar X, which lends itself to K less than 1. Now, what if it's 0? 0 is just a number. Well, in that case, absolutely. This is at equilibrium. And also K equals 1. This is a special case, and you'll hardly ever see it because there are very few real-world examples wherein the standard state of a reaction is also equal to the equilibrium at which that reaction lies. So these are 3 sets of conditions that will come in pretty handy to us. Okay, so now here, I wrote down Q, bless you. Talk about Q a little bit more. Were you guys exposed to that earlier in the semester, maybe last semester? Okay. So Q is going to take the same form as K. 3 equal signs, always, for this system. Concentration of Z divided by partial pressure Y times concentration aqueous X squared. Now, Q is not K. It takes the same form, but the 2 are not going to be the same unless we are at equilibrium. What Q tells me is where my reaction is going to go given a set of conditions. So in the standard state, all these are going to be 1, for example. But I could make up any different number of concentrations for all 3 of these species. They can be different, they can be the same. Doesn't really matter. But we want to remember what Q tells us. So if Q is greater than K, what does this mean for my reaction?
Proceeds in the reverse direction.
Proceeds in the reverse direction. So I'll just draw an arrow pointing to the left. Reverse reaction is what's going to occur. Q is less than K. The exact opposite is true. Forward reaction occurs. This is what Q tells us. Now, this is going to be important. Dr. Horvath gives you guys a reaction, and you're not in the standard state, and he wants to tell you, he wants to say, how many moles of this product am I going to have left over? You're going to need to do a Q analysis before you start doing any chemistry, and that'll tell you, well, okay, is my reaction going to go to the left or to the right? So I know to add or subtract from the variables I've set up to solve my problem. Q is super duper handy. Remember, it takes the same form as K, but Q is only equal to K when what conditions apply? EQ. So there's your brief refresher on Q and K. All right, now we're going to talk thermodynamics. We're also going to talk Q. So, Dr. Horvath gives us, we won't go ahead and derive it because we're not physical chemists yet. Gibbs free energy of a reaction in the standard, of any reaction, I'm rearranging it. Gibbs free energy of any reaction is equal to Gibbs free energy of that reaction in the standard state plus 2.3 RT log Q, my reaction quotient. Now, going through this equality, I have a tool to determine spontaneity of any reaction, even if it's not in standard conditions, because I can solve for GR, standard state. I can figure out Q by writing K, and then putting in the numbers that are not equilibrium values. And then I can figure out where this reaction is going to go. Left, right, spontaneous or non-spontaneous, as written at concentrations defined by Q. Now, this is our first step. Delta GR, any reaction. Okay. So, we go on, page 2111. Connection between Gibbs free energy in the standard state. Take another look at those two paragraphs there, chapter 21, after Dr. Horvath shows you guys the example. That'll make a lot more sense once you guys have seen it. Okay. So we're talking about Q still. If every term in Q is equal to 1, I know Q equals 1, and these conform to standard state conditions. Now, if Q is equal to 1, what's log Q? Log Q is 0. So, Q equals 1, standard state conditions. So the math tells me GR for this reaction is equal to change of Gibbs free energy of the reaction in the standard state. Just by the numbers. Just doing some simple logarithm math. Now, suppose each value in Q is an equilibrium value. Now if this is true, Q equals K, takes the same form as K, so if I put equilibrium values in here, Q is going to be equal to K, and the Gibbs free energy for that reaction is equal to 0. So, at equilibrium, we'll start writing. So at equilibrium, Gibbs free energy of the reaction is written as 0. But I know that's also equal to Gibbs free energy in the standard state plus 2.3 RT log Q, but in this case, K. So, at equilibrium, rearranging this, we get Gibbs free energy standard state for any reaction at equilibrium is equal to negative 2.3 RT log K, which is really just log Q, but all the values in Q are equilibrium values. Takes the same form, numerically equal.
Since K is equal to 1, the log 1 is 0, that's why it's equal to 0, right?
These are two different situations that I'm dealing with here. So if K were equal to 1, then Gibbs free energy of the reaction in the standard state would be 0. That's a special case. So what I'm saying here, two different things. If Q is equal to 1, and we're not at equilibrium, then I'm in the standard state. So Gibbs free energy of whatever reaction I'm running conforms to Gibbs free energy of the standard state. But if I'm at equilibrium, these don't have to be 1, and as a matter of fact, they rarely are. So at equilibrium, I'll notice that Gibbs free energy of whatever reaction I'm running, concentrations again don't all have to be 1, is equal to 0. Because my tendency to proceed is the exact same as my tendency to reseed in the reaction. So I can use this equivalency, subtract off 2.3 RT log K to give me this relationship. So these are two separate cases. They can be the same, but very, very rarely are. That bottom scenario. Okay, let's see here. So this relationship is very useful because it allows us to get GR standard state for reactions that we can't measure at the standard state. For example, what we were just talking about. Calcium ion plus carbonate ion to give me calcium carbonate. I've erased it, but it's right there at the bottom of page 2111. I know I can't prepare standard state conditions because the second I have calcium and carbonate ion in appreciable concentrations, they murder each other. I make calcium carbonate. So I can have both of those at a concentration of 1, which conforms to the standard state. So what I do is I use this relationship and I figure out what K values are, and then I can go through the quick math to give me the Gibbs free energy of that reaction in the standard state without actually having run it. So we can get that indirectly. Okay, question 21-23. And this sort of addresses the question we just had before. If Gibbs free energy of the reaction in the standard state is 0, K equals 1. That's the special case that we were talking about before, where both of these are going to hold true because log 1 is just 0. So that's a special case, combination of what we have in Horvath's bolded case 1 and case 2 on page 2111. All right, so let's see here. What else do we have here? Therefore, if I want to take advantage of this, and I want to make a general statement about the Gibbs free energy of a reaction, I can do that. Gibbs free energy of any reaction is negative 2.3 RT log K, which is just equal to Gibbs free energy of a reaction in the standard state. Plus, where do I have it written down? Oh, good, nowhere. Okay. Plus 2.3 RT log Q. So if I know what equilibrium concentrations are for whatever reaction I'm running, and I know what concentrations I currently have, I can go through and I can solve this to directly get it Gibbs free energy of a reaction that is not in the standard state. So, if you're a little bit more savvy with logs, Dr. Horvath gives it to you in the book. You know that this entire thing, I can combine my 2.3 RT terms and my log terms to give me 2.3 RT log Q divided by K. That makes it look a little bit smaller, but if you're not comfortable with this, you can use this one, that's fine. That's one that's more easily derived. But again, that's just log math that gives you log Q over K. So there's our general scenario. This is a little bit more specific. We're in Q equals K. That's how I got there. A couple steps of derivation. I think you guys are given a lot of this information on your sheets, are you? On your info sheets? You're given all the standard thermodynamic information that you need. So, it's good to know how that stuff was actually conceived, though. It's important to understand the relationships between delta G0, Q, and K. Because, once again, this is all just a study of thermodynamics. Equilibrium, all that stuff we've been doing all semester, that was all conceived after thermodynamics. All right. So, any questions on this stuff right now? We're going to get into a couple of examples that will help us apply this. Okay. So, we're going to consider, well, we already know what happens with Q and K. We already talked about that over here, a little bit over here. Consider the thermodynamic analysis of the following reaction at 25 degrees C. So, calcium carbonate, decomposition, not dissolution this time. So I'll take solid calcium carbonate, and it's just going to decompose into solid calcium oxide and CO2. Now, if we think about this reaction at room temperature, for starters, I realize I've got a lot of calcium carbonate here, and not all of it's falling apart. So, quick real-world example. This reaction is actually pretty hard to run, and that's based upon the fact that, once again, you guys are exposed to calcium carbonate every day, and yet in this room, which has a bunch of calcium carbonate in it, we don't suffocate from CO2. So, first off, write thermodynamic K for this reaction. What's K equal to for what I have written down here?
Pressure and CO2 gas.
Pressure, gaseous CO2. That's all K is. All right. Now, I'm not given any numbers for K. Not in my information sheet. Dr. Horvath hasn't given it to me on the test, that jerk. How are we going to get at figuring out whether this reaction is spontaneous, favorable? Am I going to have a lot of calcium oxide and CO2, a little bit of it, none of it at all? Question 2125. Use appropriate data from table 21.1 to calculate HR and SR for this reaction, standard state. Then calculate Gibbs free energy standard state from those values. Let's do it. More practice we get, the better. Okay, start with calcium carbonate. What's the heat of formation of calcium carbonate?
Negative 1,207.
Negative 1,207 is what I got. And the standard entropy, calcium carbonate? 90.0? 98.0. 9.80.
90.8.
90.8. Great. All right. Now, calcium oxide.
Enthalpy negative 66.0. Entropy 39.75.
Thanks for spoon feeding it to me. Okay. CO2 now.
Enthalpy negative 393.5. And entropy positive 213.7.
Okay, remember units for entropy, joules, mole K, gonna be lazy, kilojoules per mole for enthalpy. Okay, so go ahead through, apply Hess's law to get delta HR, standard state, and delta SR, standard state. Remember to keep your signs straight. Once you get a number, just yell it out. One digit at a time.
177.5.
4? No, for which one? FOR.
There's an enthalpy.
Positive 162.7 joules. So, if you want to click that.
162.7. So if we want to convert that to kilojoules before we go into delta G, divide by a grand. Okay, so now we're in a good place to go ahead and plug this into our Gibbs free energy formula. Delta G equals delta H less T delta S. And what do we get for the Gibbs free energy at 298 K? This reaction in the standard state.
Positive 131 kilojoules per mole.
This is a case wherein temperature absolutely does matter, because I see I've got unfavorable enthalpy, I'm weakening bonds, but I've got favorable entropy because I'm making 2 moles of stuff from 1 mole of stuff, and I'm making a solid, or I'm making a gas from a solid. So in this case, temperature absolutely matters. We have to go all the way through to prove it to ourselves. And this is non-spontaneous, anti-spontaneous. at 298 K. Okay, so just gave you the answer, 2126. This reaction is anti-spontaneous under standard state conditions at this temperature. Is this because of delta HR, delta SR, or both? Delta HR is my unfavorable term, therefore, delta HR is the answer to 21.6. Okay. Question 2127. Based upon what we got here for the Gibbs free energy of this reaction in the standard state, evaluate K. Let's do it. We can use this stuff over here. Okay, so I know I've got standard state Gibbs free energy of this reaction. I don't care about temperature. This is at 298 K, but there is no standard state temperature. So this Gibbs free energy is equal to 129 kilojoules per mole. Now, I know that's equal to, from what I just erased up on the board and what Dr. Horvath had on 2 pages previous, negative 2.3 RT log K. So, Dr. Horvath gives us R, 8.314 joules per Kelvin per mole. All right, now all we have to do is go ahead and rearrange this. So, I see 129 divided by negative 2.3 times 8.314.
Should you convert 8.314 to kilojoules because delta G is in kilojoules and R in joules?
Why do that to me? 8.314. Now, you can do it either way, doesn't much matter. So, kilojoules per mole, I like to convert to joules, just to keep the 8.314 the same. And that's why you always include units while you're writing this thing, if you haven't done it a lot. Now that I know everything's going to be straight, I can go ahead through and finish up writing. So 2.3, this is a hard number that came from LN. 8.314 joules per Kelvin mole, 298 K joules per mole here. So I know all this stuff is going to work out. All right. Now the number, if you go ahead and plug this in, should give you negative 22 is what I got, 0.6. Okay, so this is equal to log of K. So what's K? What's K going to be? Is it going to be big or is it going to be small?
Very small.
Very, very small. So what's the exact number?
2.3 times 10 to the negative 23.
Now in this case, when I was talking about K, I realized that K is equal to a partial pressure. So I can attach to it the unit of atmospheres if I'd like to. Dr. Horvath goes on to explain, this is just an apparent unit, because if I have a more complex K, I'm going to have all sorts of stuff here. For a simple example, we look at question 2128. If I just double the moles of everything, stoichiometrically, this will still work. But that's going to change what my K looks like. Because then my K is going to be partial pressure CO2 gas squared. Similarly, if I divided everything from there by 4, I would have root pressure CO2. So you can end up with some really weird units here, but it's generally a good idea to take a look and see what K is actually trying to tell you. In this case, we can relate it directly to a physical unit that we know well, partial pressure, but in some cases it's a little bit more awkward. But always take a look at that. Attaching apparent units to K is a good exercise and is often valid. All right, so what this actually tells us, this K value, we realize this reaction is not going to run very well as written. Similar to dissolving calcium carbonate. KSP is very, very small, so I don't end up with a lot of calcium or carbonate ion. In this case, K is very, very small. Not a lot of calcium oxide, not a lot of CO2 floating around if I have a closed system that contains calcium carbonate. Okay, so to proceed, reconsider that same reaction we have up there, for which K is that number. And at 25 degrees C, recognize that this K means that if I take pure calcium carbonate and I put it in a glove box devoid of any gas of consequence, this reaction is going to be spontaneous up until I reach this condition. Now we realize that's an incredibly, incredibly low pressure of gas. And what we're going to do today is we're going to talk about exactly how much carbon dioxide that is. So, does anyone have any questions regarding what we ended up doing here? Okay, good. So, make sure you get some practice with that. Those equations are important. You almost always have to solve one at some point during the semester anyway. So, next question, bring it on. If this calcium carbonate decomposition reaction is carried out at 25 degrees C in a 10-liter vessel that is initially devoid of carbon dioxide, calculate the number of moles of carbon dioxide produced as I establish this equilibrium. We're given the answer, but it's not about the answer. It's a journey. So, same reaction, rewrite it. So how are we going to get at the number of moles contained in this container? So let's start writing down what I know. K directly gave me a pressure, right? Volume of this container, 10 liters. I'm looking for moles, abbreviated little n. I'm also given temperature. Any thoughts? It's like Wheel of Fortune. PV equals nRT. N, or R is a constant. We know that. We know pressure. 2.3 times 10 to the minus 23. Atmospheres. We know volume. $10 liters. We're looking for N. We know R. R is given to you earlier in the book. The value is 0.084. The unit, liter, atmospheres, per mole Kelvin. Sort of a cure-all unit, but it makes much more sense now that we're applying it. Temperature, 298 K, I think. Yeah. So, somebody could go through and solve this for me? Do like
3 times 10 to the negative 24.
9.2 times 10 to the minus 24 moles from PV equals nRT, going all the way back to the stuff we swore we'd never have to remember. Okay. Next question. Follow up, question 2129, by calculating the number of molecules that correspond to 9.4 times 10 to the minus 24 moles. Avogadro's number, what is it? 6.02 times 10 to the minus 23. Now I know that there are 6.02 times 10 to the 23rd molecules per mole. Multiply that through by the number of moles. .2. So how many molecules of CO2 do I have? 5.5. Now this is a problem I have with a lot of statisticians out there that tell me that 79.5 out of every 100 college students drink on Friday night or something like that. Who's the half? The answer that I got was 5.7. So I would call it 6 molecules. I heard somebody say 5. It's between 5 and 6. That fifth, or that sixth molecule of CO2 is constantly shifting back and forth. So it's somewhere between 5 and 6 molecules in 10 liters. It's not going to be 5.5 ever, because the same way you can't have half of a college student, you can't have half of a CO2 molecule. You can have half a mole of CO2, which is what I do when I put a 1/2 in front of here. That's important to remember. But you cannot have half of a molecule, 5 or 6 molecules. So, let's see here. Can we find any of these molecules? Not a chance. 6 molecules of CO2 and 10 liters of space. There is no analytical measure at this point that is sensitive enough to find those among anything else that might be there. Okay. So, that's all for questions 29 and 30. Now, guys, for your exam on Friday, I have taken a look. It focuses on the end of Chapter 18 and the entirety of Chapter 19. That is where I would devote most of your time for study. Tomorrow, we will be doing some review. I have some questions planned that I will show you guys, a couple solutions. But come with a couple questions if you got them. I'll be happy for that hour and a quarter to answer whatever you might have. Have a good day. 20 and 21? No, they will not be focused on this exam. Study 18 and 19.